Huaynaputina. Huaynaputina is a stratovolcano and a volcanic upland in southern Peru. Part of the Central Volcanic Zone of the Andean Volcanic Belt, it is the product of the subduction of the oceanic Nazca tectonic plate beneath the continental part of the South American tectonic plate. Huaynaputina is a large volcanic crater, lacking an identifiable mountain profile, with an outer stratovolcano and 3 younger volcanic vents. During the Holocene, Huaynaputina has erupted several times, including on February 19, 1600, the largest ever recorded in South America. Witnessed by people in the city of Arequipa, this eruption measured 6 on the Volcanic Explosivity Index and continued with a series of events into March. Its impact on the region was severe. It wiped out vegetation, buried the surrounding area with 2 meters, 7 feet, of volcanic rock and damaged infrastructure and economic resources. The eruption had significant effects on Earth's climate. Temperatures in the northern hemisphere decreased, and millions of tons of acid were deposited. Floods, famines and cold waves resulted in numerous places. The climate disruption caused social upheaval in countries as far away as Russia and may have played a role in the onset of the Little Ice Age. Huaynaputina has not erupted since 1600. There are fumaroles in its amphitheater, and hot springs occur in the region, some of which have been associated with Huaynaputina. The volcano lies in a remote region, where there is little human activity. Still, there are about 30,000 people living in the surrounding area, with another 1 million in the Arequipa metropolitan area. If an eruption similar to the 1600 event occurred, it would likely lead to a high death toll and cause substantial socio-economic disruption. The Peruvian Geophysical Institute announced in 2017 that Huaynaputina would be monitored by the Southern Volcanological Observatory. Name. The name Huaynaputina was given to the volcano after the 1600 eruption. It is also spelled Huaynaputina or Huaynaputina. According to one translation, Huayna means new and Putina means fire-throwing mountain. The full name is meant to suggest the aggressiveness of its volcanic activity and refers to the 1600 eruption being its first one. 2 other translations are young boiling one – perhaps a reference to earlier eruptions, or where young were boiled, which may refer to human sacrifices. Other names for the volcano include Chekpakina, Chiquilmote, Guaida, Olmate, and Quinistac-Willis. The volcano El Misti was sometimes confused with and thus referred to mistakenly as Huaynaputina. Geography. The volcano is part of the Central Volcanic Zone of the Andes. Other volcanoes in this zone from northwest to southeast include Sarasara, Corpuno, Amparo, Sabancaya, El Misti, Ubinas, Tixani, Tutupaca, and Ucumane. Ubinas is the most active volcano in Peru. Huaynaputina, El Misti, Sabancaya, Tixani, Tutupaca, Ubinas and Ucumane have been active in historical time, while Sarasara, Corpuno, Amparo, Casiri and Chacani are considered to be dormant. Most volcanoes of the Central Volcanic Zone are large composite volcanoes that can remain active over the span of several million years, but there are also conical stratovolcanoes with shorter lifespans. In the Central Volcanic Zone, large explosive eruptions with volcanic explosivity index of 6+ occur on average every 2,000 to 4,000 years. Huaynaputina is in the Olmate and Quinistac-Willows districts, which is part of the General Sanchez Cerro province in the Moquegua region of southern Peru. The town of Olmate lies 16 kilometers, 10 miles, southwest of Huaynaputina. The city Moquegua is 65 kilometers, 40 miles, south-southwest of the volcano, and Arequipa is 80 kilometers, 50 miles, to its north-northwest. There's little human activity in the nearby area. The region is generally remote and the terrain extreme, and the area around Huaynaputina is not easily accessible. A cattle grazing footpath leads from Quinistac-Willows to the volcano, and it is possible to approach the volcano over surrounding ash plains. Structure. Huaynaputina lies at an elevation of about 4,850 meters, 15,910 feet. It consists of an outer composite volcano, or stratovolcano, and 3 younger volcanic vents nested within an amphitheater that is 2.5 kilometer, 1.6 miles, wide and 400 meter, 1,300 feet, deep. This horseshoe-shaped structure opens eastwards and is set in the older volcano at an elevation of 4,400 meters, 14,400 feet. The amphitheater lies at the margin of a rectangular high plateau that is covered by ash about 2 meters, 6.6 feet, thick, extending over an area of 50 square kilometers, 19 square miles. The volcano has generally modest dimensions and rises less than 600 meters, 0.37 miles, above the surrounding terrain, but the products of the volcano's 1,600 eruption cover much of the region, especially west, north and south from the amphitheater. These include pyroclastic flow dunes that crop out from underneath the tephra. Deposits from the 1,600 eruption in previous events also crop out within the amphitheater walls. Another southeastward opening landslide scar lies just north of Huaynaputina. One of these funnel-shaped vents is a 70-meter, 230 feet, trough that cuts into the amphitheater, which appears to be a remnant of a fissure vent. A second vent appears to have been about 400 meter, 1,300 feet, wide before the development of a third vent, which has mostly obscured the first two. The third vent is steep-walled, with a depth of 80 meters, 260 feet. It contains a pit that is 200 meter, 660 feet, wide, set within a small mound that is in part nested within the second vent. This third vent is surrounded by concentric faults. At least one of the vents has been described as an ash cone. A fourth vent lies on the southern slope of the composite volcano outside of the amphitheater and has been described as a maar. It is about 70 meter, 230 feet, wide and 30 meter, 98 feet, deep and appears to have formed during a phreatomagmatic eruption. These vents lie at an elevation of about 4,200 meters, 13,800 feet, making them among the highest vents of a Plinian eruption in the world. Slumps have buried parts of the amphitheater. Dacitic dikes crop out within the amphitheater and are aligned along a northwest-south trending lineament that the younger vents are also located on. These dikes in a dacitic lava dome of similar composition were formed before the 1,600 eruption. A number of faults with recognizable scarps occur within the amphitheater and have offset the younger vents. Some of these faults existed before the 1,600 eruption while others were activated during the event. Surroundings. The terrain west of the volcano is a high plateau at an elevation of about 4,600 meters, 15,100 feet. North of Huaynaputina, the plateau features the volcano Ubinas in the depression of Laguna Salinas, while the peaks Cerro El Volcan and Cerro Chan are situated south of it. The lava dome Cerro El Volcan and another small lava dome, Cerro Las Chilpas, lie 3 kilometers, 1.9 miles, south from Huaynaputina. Northeast-east of Huaynaputina, the terrain drops off steeply, 2.3 kilometers or 1.4 miles vertically and 6 kilometers or 3.7 miles horizontally, into the Rio Tambo Valley, which runs southward and then westward as it rounds Huaynaputina. Some tributary valleys join the Rio Tambo from Huaynaputina. Clockwise from the east, these are the Quebradas Huaynaputina, Quebrada Toril, Quebrada Aguas Blancas and Quebrada del Volcan. The Rio Tambo eventually flows southwestward into the Pacific Ocean. Geology. The oceanic Nazca tectonic plate is subducting at a rate of 10.3 centimeters per year, 4.1 in/year, beneath the continental part of the South American tectonic plate. This process is responsible for volcanic activity in the uplift of the Andes Mountains and Altiplano Plateau. The subduction is oblique, leading to strike-slip faulting. Volcanic activity does not occur along the entire length of the Andes, where subduction is shallow. There are gaps with little volcanic activity. Between these gaps lie volcanic belts, the Northern Volcanic Zone, the Central Volcanic Zone, the Southern Volcanic Zone and the Austral Volcanic Zone. There are about 400 Pliocene Quaternary volcanoes in Peru, with Quaternary activity limited to the southern part of the country, which is part of the Central Volcanic Zone. Volcanic activity in that zone has moved since the Jurassic from the present-day coast region where remnants persist in the Cordillera de la Costa eastward into the actual Andes in the present-day volcanic arc, where it is defined by stratovolcanoes. Many Peruvian volcanoes are poorly studied because they are remote and difficult to access. The basement underneath Huaynaputina is formed by almost 2 km thick, 1.2 miles, sediments and volcanic intrusions of Paleozoic to Mesozoic age including the Jura group as well as the Cretaceous Madillac Formation of volcanic origin. During the Tertiary, these were overlaid by a total of 300 to 500 meters thick, 0.19 to 0.31 miles, deposits from the Ignimbritic Capelune, Lalui, and Seneca formations. Cretaceous sediments and Paleogene-Neogene volcanic rocks form the high plateau around Huaynaputina. The emplacement of the Capelune Formation continued into the earliest Pliocene. Subsequently the Pleo-Pleistocene Barroso group was deposited, which includes the composite volcano that hosts Huaynaputina but also ignimbrites that appear to come from calderas. One such caldera is located just south of Huaynaputina. The late Pleistocene to Holocene volcanoes have been classified as the Arequipa volcanics. Local. The vents of Huaynaputina trend from the north-northwest to the south-southeast, and encompass the neighboring volcanoes Ubinas and Tixani. Ubinas is a typical stratovolcano while Tixani resembles Huaynaputina in structure. The trend also constitutes a volcanic field located behind the major volcanic arc and associated with faults at the margin of the Rio Tambo Graben as well as regional strike-slip faults. The volcanic rocks produced by these volcanoes have similar compositions, and recent seismic and volcanic activity at Ubinas and Tixani indicate that they share a magma reservoir. The faults associated with the volcanic complex have influenced the evolution of the constituent volcanoes including Huaynaputina by acting as conduits for ascending magma especially at fault intersections. A 40 by 60 kilometer, 25 miles times 37 miles, magma reservoir may underpin this volcanic system. Composition. The eruption products of the 1600 eruption are dacids, which define a calc alkaline, potassium-rich sweet. The geochemistry of the 1600 rocks has also been described as adikitic. The 1600 rocks also contain rhyolite inclusions in a rhyolite matrix. Phenocrysts include biotite, chalcopyrite, hornblende, ilmenite, magnetite and plagioclase, amphibole, apatite and pyroxene have been reported as well. Aside from new volcanic rocks, Huaynaputina in 1600 also erupted material that is derived from rocks underlying the volcano, including sediments and older volcanic rocks, both of which were hydrothermally altered. Andesite has also been found at Huaynaputina. The Huaynaputina pumices have a white color. A large amount of sulfur appears to have been carried in a volatile phase associated with the magma rather than in the magma proper. An even larger amount of sulfur may have originated from a relic hydrothermal system that underpins the volcano, and whose accumulated sulfur would have been mobilized by the 1600 eruption. Some contradictions between the sulfur yield inferred from ice core data and these inferred from the magma composition can be resolved this way. The amount of volatiles in the magma appears to have decreased during the 1600 eruption, indicating that the magmas originated either in two separate magma chambers or from one zone magma chamber. This compositional change may explain changes in the eruption phenomena during the 1600 activity as the Dacite 1 rocks erupted early during the 1600 event were more buoyant and contained more gas and thus drove a Plinian eruption, while the latter Dacite 2 rocks were more viscous and only generated Vulcanian eruptions. Crustal interactions and crystal fractionation processes were involved in the genesis of the magmas as well, with the so-called Dacite 1 geochemical suite forming deep in the crust, while the Dacite 2 geochemical suite appears to have interacted with the upper crust. The rocks had a temperature of about 780 to 815 degrees Celsius, 1436 to 1499 degrees Fahrenheit, when they were erupted, with the Dacite 1 being hotter than the Dacite 2. Their formation may have been stimulated by the entry of mafic magmas into the magmatic system. Such an entry of new magma in a volcanic system is often the trigger for explosive eruptions. The magmas erupted early during the 1600 event, in the first stage of the eruption, appear to have originated from depths of more than 20 kilometers, 12 miles. Petrological analysis indicates that some magmas came from depths greater than 15 to 25 kilometers, 9 to 16 miles, and others from shallower depths of about 4 to 6 kilometers, 2.5 to 3.7 miles. While an older hypothesis by De Silva and Francis held that the entry of water into the magmatic system may have triggered the eruption, a 2006 viewpoint argues that the entry of new dacitic magma into a pre-existent dacitic magma system triggered the 1600 eruption. Furthermore, movement of deep andesitic magmas that had generated the new dacite produced movements within the volcano. Hazards in volcanological research. About 30,000 people live in the immediate area of Huaynaputina today, although over 69,000 and 1,008,000 live in the nearby cities of Moquegua and Arequipa, respectively. The towns of Calico, Omate, Bukina and Quinistacuilas and others would be threatened in case of renewed eruptions. A repeat of the 1600 eruption would likely cause a considerably greater death toll owing to population growth since 1600, in addition to causing substantial socio-economic disruption in the Andes. Evacuation of the area directly around the volcano would be difficult owing to the poor state of the roads, and the tephra fallout would impact much of Peru's economy. The 1600 eruption is often used as a worst-case scenario model for eruptions at Peruvian volcanoes. In 2017, the Peruvian Geophysical Institute announced that Huaynaputina would be monitored by the future Southern Volcanological Observatory, and in 2019 seismic monitoring of the volcano began. In 2010, earthquake activity and noises from Huaynaputina alerted the local population and led to a volcanological investigation. As part of this investigation, seismic activity was recorded around the amphitheater. Analysis showed that seismic activity was concentrated around the amphitheater with no recorded earthquakes within it and appeared to be associated mainly with the faults and lineaments in the region. The researchers recommended more extensive seismometer coverage of the area and regular sampling of fumaroles, as well as reconnaissance of georadar and self-potential of the volcano. Climate and vegetation. Between 4,000 to 5,000 meters, 13,000 to 16,000 feet, in elevation mean temperatures are about 6 degrees Celsius, 43 degrees Fahrenheit, with cold nights, while at Omate, mean temperatures reach 15 degrees Celsius, 59 degrees Fahrenheit, with little seasonal variation. Precipitation averages 154.8 millimeters per year, 6.09 in/year, falling mainly during a summer wet season between December and March. This results in an arid climate, where little erosion occurs and volcanic products are well preserved. Vegetation in the area of Huaynaputina is scarce, and on the pumice deposits from the 1600 eruption it only occurs during the wet season. Cacti can be found on rocky outcrops and valley bottoms.